Thank you very much for the introduction. Thank you for introducing, thanks for inviting me to the talk. So I'll be talking about understanding, interpreting, and design neural network models through tensor representation. And specifically, I will probably talk about a few interesting things that my group has been recently working on for neural networks in machine learning. So let me see. Oh, okay. So yeah, I guess I don't have to motivate much about the success of neural networks. Its empirical success has been unprecedented, due to the growth of the computation power and the growth of data available. So there are some challenges in neural networks. And today I will talk about one of the challenges, which is in understanding generalization of deep neural networks. So there is this mystery of over-parameterization, which basically means the number of samples much smaller than the number of parameters for a neural network to work very well. So you can see this empirical result here. You can see a small gap between the test error and the training error, whereas a learning theory would tell you that probably you will likely to get a very high generalization gap. So there is this mismatch between empirical observation and learning theory. So there are some studies trying to fit random labeling with the training data. So essentially bad generalization happens. So DNN actually easily fits a random data, and regularization techniques does not help with generalization under those scenarios. So basically conventional wisdom fails. So under these scenarios, what can we do? Right. So there is another challenge that I'm going to talk today, which is, in robustness of neural networks, specifically deep neural networks. I guess I also do not have to motivate this very much here in this audience. If you consider an input image, in this case, let's say autonomous driving system, and you have a computer vision system that's trying to recognize, signs along your driving roads, right? So if you have an input image, a stop sign, and some kind of perturbation, could be adversarial, could be even just different weather or different sticker on the stop sign. But anyhow, some kind of adversarial noise added to the image. And then your computer vision system, which usually consists of a deep neural network, all of a sudden would classify a stop sign as a yield sign. Right? This is really dangerous, especially for these high stakes tasks. So reliable AI not guaranteed yet. So what do we do? This is the outline of what I will talk about today. Basically, I'll talk about a recent work published in AI Stats 2020 about a generalization in deep neural networks using tensor representation. And I'll also talk about a recent work that is under submission for interpreting and improving transformers, which is a very popular neural network that's been hugely successful in language models and also been very successful recently for image data and the graph data. So then lastly, I will also briefly talk about a recent work that's also under submission from my group working on robustness of deep neural networks. Okay, so, well, again, just to remind everyone, we see this mismatch between empirical observation and learning theory. Basically, the deep neural network models are in principle rich enough to memorize the training data, while under the scenario, usually the number of parameters is much larger than the number of examples. However, in practice, they do not overfit. Okay, so conceptual challenge to statistical learning theory. Traditional measures of model complexity struggle to explain the generalization ability of large networks, and yet we have to find a measure under which these enormous models are simple. So based on this idea, also based on the idea that there are some computational challenges in large network, we're going to propose something. So what is this computational challenge? It's basically saying that during test time, if you have a large neural network that you have to deploy for every single unseen image that you have to predict, or every single unseen other input data you have to predict, require a large amount of computation and memory storage. this is really ill-suited for smartphones or internet devices, which has very limited memories and power, right? So, and also what's worse is this is really a repeated cost. So there comes a question, right? How to explain generalization ability? Are there effective capacities that we know how to explain the generalization? Can we compress the neural network for computational efficiency? And then can compression be used to understand generalization, or how to compress the neural network without much performance loss? So our goal here is to better understand generalization. So we basically wanted to derive efficient and provably correct algorithms that reduce the number of parameters in the nets and yielding generalization bounds that are better than naive parameter counting, of course, depends on simple and intuitive measurable properties of the data of the network and empirically correlated with generalization. So with this goal, we also hope that we can get more efficient model and, and we can do faster prediction during the deployment time or test time, right? So goal is, can we get fewer number of parameters? Can we preserve high expressive power, meaning high performance under those smaller models? And, do we still have to do fine tuning, which is quite expensive? Can we just, not do those kind of fine tuning stuff as people usually do in this compression-based methods? So we wanted to find a simple compression framework for providing generalization bounds. Okay, so just a little bit background knowledge. So we wanted to characterize generalization using a compression-based framework. And let's say you have a compressible network. So if you have, basically you wanted to define the compressible network based on the sample, a sample of a bunch of examples. So a sample with m examples with, for a deep neural networks greater than small m such parameters, you define a compressed network, which is G, with Q parameters at most, R discrete values. You define it such that the original prediction and, the difference between the original prediction and the compressed prediction is going to be very small based on the sample set. So, I do not care about other examples. I only care about my similarity of the compressed network and my original network on my sample set. Okay, so based on that, we will use learning theory to find a generalization bound, which basically says that, if you wanted to characterize the generalization error or the expected error of the compressed network, then it's gonna be upper bounded by some marginal error of the original network. So it's like on the training examples, but a little bit more strict than just evaluating the traditional error on the training examples on this original model. And then with a complexity, which basically measures the complexity after compression. So this is a very intuitive bound. And the idea is that we're going to use that bound to give a better generalization characterization combined with tensor representation. So can we design compression techniques that reduce the actual number of parameters and speed up prediction? Can we still provide theoretical guarantees for such compression? Can the compression depend on simple, intuitive, and measurable property of the network? So just a review of compression methods that are commonly used. For example, you might have heard about pruning, quantization, encoding, and knowledge distillation. Most of the existing methods might fall into that. But there is a line of work which is called low-rank approximations. So it's basically complementary to other techniques I mentioned above, but it reduced the number of parameters by a factor polynomial in the dimension. So that's nice, but there is a caveat. Only when the weight matrices are actually low rank in convolutional neural network case, which is usually the most popular neural networks that we use recently. Usually those are convolutional kernels. And it's really hard to say whether those convolutional kernels are actually low rank. So basically, simply by assuming low rankness might not work. So the idea or the question here is, can we exploit other invariant structures while low rank approximation? Well, such as periodicity, modulation, or other things. So actually, I wanted to start with the proposition of the CP layer. So it's a very simple, since everyone is familiar with tensors here, so it's like a CP form of the tensor. So basically, we're saying that this CP layer is such a layer that represents a given n-order weight tensor with R sets of components denoted by this lambda scaling factor and the VJs, which are the components. Okay, so essentially the kernel is gonna have this CP form here. So the parameters of the network essentially becomes lambda and the VJs rather than the kernel K. Okay, so this is the CP layer. You wanted to learn them from scratch, maybe, right? So actually, very interestingly, we observe in this real data, sets, if you evaluate the so-called low ranknesses of these networks for a traditional neural network on image data, it actually doesn't really exhibit low rankness, as you can see here. The blue lines are actually the original one. But if you actually design your model using this reparameterization of the CP layer, actually becomes really low rank. So this is really surprising. Well, so going back to the caveat I said before, seems like low rankness was not necessarily already obtained. Assuming them away was kind of not practical. But here, even if you do a simple CP layer kind of learning, the learned network shows low rankness. But that's not enough. Can we exploit more structures in these kernel tensors so that we can actually, more aggressively utilize the power of low rank approximation? Answer is yes, indeed. We actually tried a bunch of ideas. One of them worked really well, which is a simple reshaping idea. So the reshaping just says that, based on this very simple toy example, you can see you have some invariant structures. In this case, I have a toy example for you to see how we can utilize, this power of reshaping to get low rankness. So let's say you have periodic structure or some kind of modulated structure. Then if you reshape this very long sequence into like a matrix, so basically it's like a lower order tensor to a higher order tensor, it turns out this higher order tensor would exhibit some low rank structure, whereas the lower order tensor does not necessarily have that. So this is really interesting. Based on this idea, we hope that we can reshape those neural networks, which are originally 4-order tensors here, into maybe, 8-order tensor or something higher. So, hopefully that would give us more compact representation. And then let's say you do CP decomposition on the reshaped kernel, theoretically, you will see the number of parameters you need is drastically smaller, under the case that it is actually low rank, and it seems like it's more likely that these kernels will actually be low rank. Okay, so we also have a main theory about the generalization error bound, which basically, implies that, we can get some measurable network properties that determine the rank we needed for this generalization bound. And essentially, here you can see some kind of visualization of these measurable properties. So basically, the remark here is that we have defined these measurable properties for the network, and using smaller values of them, basically you can see smaller values of these three would basically means that you have highly compressible networks. And you can see if you compare these well-trained and the corrupted data, then you can see indeed those well-trained models would exhibit a much better property by measuring these measurable quantities, right? So it basically means that they were highly compressible and also implies that you have tighter generalization bounds. Okay, so some performance, for example, compared with traditional neural nets on some kind of very popular benchmark data sets such as CFAR10 imaged benchmark data set, our CP layer neural network actually achieved comparable expressive power. For example, you can see with basically, you can achieve like 100% training accuracy and very impressive test accuracy, although you're doing a lot of compression. And also we wanted to evaluate the bound we gave, and it turns out the generalization bound is really matching the trend of the generalization error you observe in practice, and actually predict the generalization errors especially well at the beginning and the end of the training, which is, I think, a very nice property. And also it seems to be a little bit tighter than the previous state of the art. So some more experiments show, under a label noise setting, you can see CP layer actually achieve much better generalization under various label correction ratios. Again, here you can see a uncompressed neural network achieve 93.2 accuracy, but if you use some kind of reshaped CP, you can get a 91.28% accuracy using only 10% of the parameters. And here you can also scale it to ImageNet. So that is what I wanted to say about the generalization in deep neural network. And this is a work actually, we did in AI Stats 2020. But now I wanted to talk about our recent work on interpreting and improving transformers. So we all know that multi-hat self-attention units has been really popular these days. It's been really helpful or powerful in a lot of applications. For example, language models, audio models, image data, graph data, and so on. So, when I first look at these self-attention units, I was really confused about those because I think, the way that people show it with these diagrams, for example, I show here, and some kind of equations coped with these diagrams, sometimes it's not very easy to understand. And not, so that's why I had this idea that we really don't have a rigorous visual interpretation of these transformers, although they were so powerful. So I wanted to understand more about it. And also, when I first learned the multi-hat self-attention, I wasn't really sure, why it is introduced. Was it introduced purely for a, for a reason of parallelism, right, for efficiency of computation? So that was very unclear to me. And also that's one of the motivations of this work. We wanted to understand the multi-hat self-attention better, right? So scalability is also a concern. As you can see, recent 2 years, there's lots of work on trying to improve the efficiency of transformers, and lots of societal discussions about, the ethical issues in, running these models. They are just so expensive to run. So existing works really focus on the efficiency with respect to the sequence length, right? So how long are your sentences and so on. But what about the model parameters? Can we also work on improving the number of model parameters you need for transformers? So that is basically the incentive of this work. We wanted to have visual.
Sorry. So there was a question in chat. I'm not sure if you want to take it now or later, because I think it was about the previous part of the talk. So the question was, or the comment was, it's a nice result, and whether you could give any intuition behind the CP layer compression for neural networks.
Oh, the CP layer compression.
Yeah.
So I think there are two ideas behind that. It could be like a teacher and student network. So it's a knowledge distillation. You can use CP decomposition. But here I'm actually using CP representation, and more precisely reshaped CP representation. So that means I'm actually training from scratch without, the need of a teacher network. So that's probably a little bit different from how people would do using tensor decomposition.
So I'm not sure Andrew does to answer your question. Maybe the direction was a bit more like, why does it work so well? Whether you had any intuition about this?
I think the reshaped CP works very well compared with the CP. So as I said, like the reshaping is really like simple, a very simple idea, but actually very effective.
All right, maybe that's a good thing to discuss more later. Thanks a lot.
Thank you. So here, continuing on the discussion of the transformers, I wanted to have a rigorous visual interpretation of self-attention. And actually, I'm going to use tensor diagrams. I think many of you might be already familiar with tensor diagrams, but I still wanted to introduce them very quickly and give you some ideas of why I think tensor diagrams are very powerful in terms of helping us understanding transformers. So in tensor diagram, I think it's really like a rigorous graphical representation of operations, especially suitable for multi-dimensional arrays and higher order tensors. So, arrays are denoted in tensor diagram as nodes with legs. So for example, if scalar with no legs, vector with one leg, matrix, 2-order tensor, 2 legs, and 3-order tensor, 3 legs, and so on, right? You can represent any order tensor really efficiently and effectively using a node with legs, right? So, and also it's nice that the legs are orientation invariant. No matter where your legs are, you are representing the same tensor. So also the operations in the tensor diagram are denoted as edge connecting the node legs. So here I'm showing so-called, actually I think this is not a commonly accepted terminology, but I just for simplicity called mode RR contraction here for these two tensors. You have a tensor X. You have a tensor X, which has 3 nodes, 3 legs. So it's the 3rd order tensor. You have another 3rd order tensor. You wanted to do a contraction between the mode R here and the mode R here. Okay, so, then doing contractions, simply just connecting the 2 legs with an edge. Okay, so, and then the result becomes really simple. You can just simply, merge these 2 nodes and, delete the edge that is already being contracted out. And then the dangling legs are essentially the result. So you can very intuitively see the dimensionality of your result after you do the contraction. Similar here I'm showing a batch, multiplication. I call it mode RR batch multiplication. Basically, you'll get a tensor result, which is essentially doing an element-wise multiplication between the 2 modes here. Okay, so you can see, you can count the dangling edges or dangling legs. So it's 1, 2, 3, 4, 5. So you will have a resultant tensor with, 5 dimensions or order 5 tensor. Okay, so with this, I call it rigorously visual interpretation. Then, I wanted to introduce a little bit about the benefits of tensor diagram. As I already said, orientation invariant is a benefit. And you can explicitly see the mark of the dimensionality here. Unlike mathematical formulations, you don't have to carefully order the modes of the data objects, right? Sometimes when I was reading transformer papers, I got confused about whether this is a column major or row major, whether you denote the word as a row or denote the word as a column. So it's sometimes quite confusing. And also, with this orientation invariance, you do not need multiple mathematical notations for a simple thing along a contraction between A and B. Sometimes you might do AB, BA, or AB transpose, A transpose B, right? All of them would be universally represented as a tensor diagram with A, B, and the line connecting A and B. Right, so, and also is easy notation for multilinear operations, right? Different legs and modes can operate on their own, right? So a resultant while node merging is also a convenient thing because you can just merge connected nodes and output dimension is represented as the dangling legs, right? So evaluation of a series of operations can be denoted as a multi-step merging of the nodes. So that's really convenient. I think it's a very intuitive way of understanding math rigorously. So after my advertisation of the tensor diagram, now coming back to the self-attention, let's start with the single hat self-attention. So basically the scaled dot product attention, as you can see, the hat here just means like a single hat eye. You have a softmax function, connecting some feature representations. They call it query and key of these data. So essentially, if you understand it, it's really, the query is just X multiplied with like a feature map. And the key is also X multiplied with the feature map. X is now your input data, right? So actually, you can see a rigorous visual representation of it becomes this tensor diagram here. So first, forget about the dashed box here. This is nothing but a softmax, but focusing on the black ones. So you can see you have X and you have X and you have X. It essentially becomes a multilinear operation on X, although you have this nonlinear activation here. So, but more importantly, you have very simple ways of denoting, these, transformations, linear transformations for each of the axes and how they actually interplay with each other. So it's very, intuitive based on this tensor diagram. I listed some advantages here, it's invariant to arrangements of the input data matrix, and the model size is explicitly shown, and softmax constrain the evaluation ordering of the graph. Okay, so now you can see like the multi-hat self-attention is actually written as concatenation of these hats and multiplied with like a WO matrix. So how do you denote it using tensor diagram? Actually, one thing you wanted to notice that is the modes along which the data X contract with the weights are actually unchanged. So you can see here, you have multiple hats here. I'm just trying to draw multiple hats here. And now what you do is you stack the weight matrices, WQ, WK, WV, and WO from multi-hats as third order tensors. Before they are matrices, right? They have two legs, but now they're third order tensors, and therefore you can represent them using three-legged nodes in your tensor diagram. Okay, so now you have this extra leg here. Now what happens is that the mode D of WO and WV are actually constructed based on the equation. Also, very interestingly, you can see the concatenation of the hats, the H feature maps followed by construction with the mode H of the WO is actually equivalent to a construction along the mode H of all the weight tensors. So you can see you have 4 weight tensors here becomes a contraction along the mode H of all the weight tensors. So that's a really interesting observation. It turns out we can have a very simple representation of the multi-hat attention, although sometimes it is a little bit hard to understand intuitively. Okay, so after this tensor...
Just a quick heads up. So we have about 2 or 3 minutes left.
Oh, okay. Yeah, sure. No problem. So let me wrap up this. So for the original multi-hat tensor diagram, so we wanted to understand the role of the multi-hat H, the role of feature dimension, are they necessary or are they both necessary? Which one is more crucial? So it turns out, we wanted to understand this from the intuition that you wanted to have a holistic understanding, consideration of the weights of these, weight tensors. So it turns out we wanted to propose a new design of a multi-hat self-attention. It actually applies to any, self-attention units. So what we do is we essentially remove the lossy and redundant. We claim is actually redundant. We can actually prove it. I'll show it in a minute. The lossy and redundant dot product or contraction in attention units, and we can maintain the role of the multi-hats. So also, you can either choose to discard it. So that means that you will have a model compression because your models would be 1 over D. You only have 1 over D such number of parameters compared with the original model, or you can choose to merge it you can reshape that third order tensor into like a 2-order matrix, and then it actually becomes a CP form. So coincidentally, it becomes a CP form, but also, as you can imagine, if you do a holistic consideration of the weights, it actually becomes a tensor, and you can use tensor representation to understand how to represent that tensor. So it turns out, as I said already, right? So you can have improved expressive power. You can prove that under the same number of parameters. Basically means that this R here becomes DH, or you can maintain expressive power by just removing these edge. So essentially you would save 1/d such parameters. Yeah, you only need 1/d such parameters essentially. So you can see some really good results here by doing this, lossless multi-head design. We can get very, very good results, using these different data sets like, language model, neural machine translation, image generation. And you can also see we can maintain a 95% of the performance using 2% of the parameters. And essentially also here for these other tasks. So I'm going to skip here and maybe wrap up for the final thing I wanted to say here. So what I was planning to say is that, I'm also going to talk about a tensor representation used for robust learning in deep neural network. And, basically we design an orthogonal neural network, which is for free. So you do not have to do SVD or any additional computation cost. Your model design using tensor representation actually becomes an orthogonal, and you can establish an equivalence between orthogonal convolution layer in the spatial domain and a para-unitary system in the spectral domain. So this is we also consider like a complete characterization of all para-unitary systems, which essentially guarantee the expressive power of the orthogonal convolutional neural network. And finally, we also did a bunch of implementations, discussions to make it work in practice. So as you can see, the results are really good. Like our network can concentrate to like a Lipschitz 1 essentially with orders of magnitude smaller variance compared with other methods. And finally, we can also get very good results in terms of the clean accuracy and the robust accuracy, almost state of the art, without any need for adversarial training or these kind of other requirements. So that's my summarization. So I talked about generalization, interpretation, and I didn't have time to talk about the robustness. But going forward, I would really like to understand how to improve generalization, combining other compression techniques, and how to improve the interpretation of existing neural networks, maybe with extensions to graph data. And finally, for the robustness of the deep neural networks, I wanted to understand whether we can make this threat models more realistic. For now, we're considering like an L2 norm attack, but I wanted to understand whether we can generalize to other attacks. So yeah, that's all I have to say. Thank you.